Hey everyone. Last time we were discussing the exponential function, and so I want to continue with that discussion. We're not done yet. So let me just remind you, so let's say recall that for b, remember we want b to be a positive number, and we're not interested in the case when the base is equal to 1. So for b, a positive number with b not equal to 1. The exponential function f of x equal b to the x is, now we didn't say this out loud, but this function is 1 to 1. Now, how can you see that? Well, you can see that by just looking at the graph, right? So the exponential graph, depending on what the value of b, either looks like this or like this, right? So in either case then, right, here this is the case y equals, so either case, this is y equals b to the x, this, b to the x, this is when b is greater than 1. This graph over here is the case where b is between 0 and 1. In either case, though, we can see that the graph will pass the horizontal line test, and so that tells us that the function is 1 to 1. And the reason that we care about 1 to 1 functions, if you remember, that means that the function has an inverse. So we can say, so f inverse of x exists, and the inverse of the exponential function has a name. It's called the logarithmic function. And so the inverse is, let's say it like this. The inverse of the function f of x equal b to the x is called, so this is the logarithmic function. With base b. And so what we have is our inverse function, f inverse of x is, we write this log with a little subscript b of x. Okay, so what does that mean then? Right? What's the relationship then between a function and its inverse, in this case the relationship between b to the x and log base b of x? Well, what we have is that log base b of x equals y if and only if b to the y equals x. That is the connection that we have between a function and its inverse, right? And so this relationship right here, that captures everything that you need to know about the logarithmic function, right? And its relationship to the exponential function. In particular, so some consequences of this. So one thing that we see, log base b of b has to equal 1. And let's just try a couple of examples now. So the first one, log base 3 of 81. Well, that's equal to 4, and the reason, why is that? Because, so let's say because 3 to the 4th is equal to 81. Another example, log base 2 of 32 is equal to 5. Why is that? Well, because 2 to the 5th equals 32. Anytime when you have a function and its inverse, there's cancellation equations. So the corresponding cancellation equations so what do we have? Log base b of b to the x has to equal x, and log b raised to the log base b of x equals x. Right? So those two equations right there are the corresponding cancellation equations when we're working with the exponential and the log function. And one thing to notice here, right? I mean, logs, they can be kind of mysterious, but this tells us that the connection, or one of the reasons that you might care about the log function, is that it helps you deal with exponents, right? That can, sometimes exponents cause problems, and we'll see this, right? They make things more complicated. Log functions allow us to deal with exponents that are causing us difficulty. So, for example, let's solve the equation 2 raised to the 3x minus 1 equals 5. So here we need to figure out what x value satisfies this equation. The way to do this is to use a log function. So if I use log base 2, and I do that and I apply that to both sides, all right, we get log base 2 of 2 raised to the 3x minus 1 equals log base 2 of 5. Now, from our cancellation equations, what we get on the left-hand side, this becomes 3x minus 1. And now we can easily solve for x. So this tells us x will be equal to 1 plus log base 2 of 5 divided by 3. Okay? So remember this. We're going to use this numerous times. Logs help us deal with exponents. Now, the log function is defined for any choice of b greater than 0 as long as it's not equal to 1. Right, but the ones the base greater than 1 is really the important one in calculus. Right? So first let's look at graphs of logs. Now and I just want to consider the case where b is greater than 1. The exponential function has a graph that looks like this. So this is y equals b to the x in the case that b is greater than 1. It passes through the point 0, 1. And remember what you need to do if you want to find the graph of the inverse function, you reflect it about the line y equals x. And so the corresponding graph, when reflected about the line y equals x, now it's going to pass through the point 1, 0, and so this is the graph y equals log base b of x, right, for the case b greater than 1. And this is the one that we're going to be concerned with. This leads us to certain properties of logs. Some of this I think will be review for you, hopefully. So let's say properties of logs. So let's let b be greater than 1. The function f of x equal to log base b of x is 1 to 1 and continuous with domain. Remember, when you're working with a function and its inverse, the roles of domain and range get reversed, and so it's continuous with domain 0 to infinity. That's the range of the exponential function, and the range of the log function is going to be the domain of the exponential function. So the log function has domain 0 to infinity and range all real numbers, minus infinity to positive infinity. Also, so now there's some properties here. The first one, if you look at log base b of x times y, that can be rewritten. That's equal to log base b of x plus log base b of y. And this reflects this notion, right? So the connection between the log and the exponential function, you can think of the log function as the exponent, the corresponding exponent. So log is an exponent. And then what happens when you multiply, right? So if you do b to the x times b to the y, what do you do with the exponents? You add them. That's exactly what this is telling you right here. Right? When you multiply an exponential function, you add the exponents. If you recognize that a log is the corresponding exponent, then that's exactly what this rule is telling us. Part B, log base b of x divided by y. Well, what happens when you divide exponentials, b to the x over b to the y? You subtract the exponents. And so what we get here is log base b of x minus log base b of y. Property C, log base b of x, let's say this a little better, x raised to the y power. And let me put parentheses there. It's x raised to the y. That can be written as y log base b of x, and you should think about what the corresponding exponential rule is, right? What is that? We know that b raised to the x, or b to the x raised to the y is equal to b to the xy. It says multiply the exponents. Multiply the exponents. A couple more properties, and you can see these from the graph. The limit as x goes to infinity of log base b of x is equal to infinity. And the last one, the limit as x approaches 0 from the positive side of log base b of x is equal to minus infinity. So what that tells us is then the log function has a vertical asymptote at 0, right? As we approach 0 from the right-hand side, right, the graph is dropping down to negative infinity. There's one special case. We're dealing with logs, so special case. And that's when our base is equal to e. In that case, then, the logarithmic function is called the natural log. So the logarithmic function with base e is the natural logarithmic function. And so natural logarithmic function, and the way we do that, you'll never write log base e of x, right? It's always written ln of x, right? So the notation is right there. ln of x means log base e of x. And when it turns out that in calculus, this is really the only one that matters, the one that we really care about. And here's the reason. Well, let me just right before I go on. So the cancellation equations in this special case, natural log of e to the x equals x, and e to the natural log of x equals x, right? So those are the corresponding cancellation equations. In particular, the natural log of e is equal to 1, so there's something to be aware of. Now, everything can be phrased, when it comes to calculus, or really in all of math, everything can be phrased in terms of natural log of x. And so, let's see how that goes. Y equals log base b of x, if and only if. So here's the connection between the log function and the exponential function. So this is if and only if b to the y equals x. And now what I want to do is take the natural log of both sides of this equation. And so this is if and only if natural log of b to the y is equal to natural log of x. Now I'm going to use one of our properties of logs. This is, I guess it would have been property C. I can bring this exponent out so we get y natural log of b equals natural log of x. So this was, right, going from here to here, that was property C of logs. And now if I solve, what we get is y equals natural log of x divided by natural log of b. So what we just derived here is what's called the change of base formula. Log base b of x is equal to natural log of x divided by natural log of b. Right, so this is called the change of base. And what that tells us then is that anything that is expressed in terms of base b can be re-expressed in terms of natural log. So we can do everything with just base e. Okay, now so far we haven't done any calculus when it comes to log functions. Well, I guess we said it's continuous, but other than that. Okay, so now it's time to look at derivatives. So derivatives of logs. So we're going to do this in two steps. So first step, we're just going to look at the case, the natural log function. So if y equals natural log of x, then, right, the relationship is that e to the y equals x. And what I'd like to do is take the derivative here using implicit differentiation. So the derivative on the left-hand side, remember how implicit differentiation goes, this will be a y prime e to the y. The derivative on the right-hand side is just 1, the derivative of x. And then if I solve, what I get is y prime equals 1 over e to the y, which we know is equal to x. So what we just showed is that the derivative of the natural log of x is equal to 1 over x. Okay, so we've found a formula for the derivative in the case that we have base e. We do want to generalize this, so let's look at step 2. If we have y equals log base b of x, then what we're going to do is apply our change of base formula. So that's equal to natural log of x divided by natural log of b. And be aware, b is a constant, so that means that natural log of b is a constant. So then, y prime of x, taking the derivative here using this formula, will be 1 over natural log of b. I guess I usually write it with the x first, so it'll be x times natural log of b. So what we have then, our more general formula, the derivative of log base b of x is equal to 1 over x natural log of b. On a quiz or a test, you're not going to get a question that says compute the derivative of natural log of x, but you will be asked to use this formula in conjunction with a chain rule. So let's write down the formula then with the chain rule. All right, this is the important one. So the derivative of natural log of f of x, where f of x is some differentiable function. According to the chain rule, what do? You take the derivative of the outside function and plug the inside function back in. The outside function is natural log. If we took the derivative, we get a 1 over x, but plug the inside function back in, and then multiply by the derivative of the inside function. So that would tell us that we get an f prime of x over f of x. You will need this formula lots and lots of times. And here's one thing to be aware of. Students, there are some students who don't learn this rule. And so when they're asked to take a derivative, right? They screw it up and they just applied this formula. Remember that when you have a function inside a log, you've got to use the chain rule. There's the formula. And then there's the general formula. If you want to do, I'll give you the general formula for base b, so log base b of f of x. The derivative is going to be an f prime of x, and then we'll have an f of x times natural log of b. This one comes up less in calculus. This first one is the one that we use mostly, but you do need to be aware of how to use this one also. So, for example, let's compute the derivative of the natural log of tangent of x. So I'm going to use this formula right here. Take the derivative of the inside, that goes in the numerator, so we get a secant squared of x, and then we just put the function itself in the denominator. And let's do an example with a base other than e. The derivative of, let's do log base 4 of x cubed plus 4x squared plus 1. So according to our formula, we put in the numerator the derivative of the inside function, so that'll be a 3x squared plus 8x. In the denominator, we put the function, so that's an x cubed plus 4x squared plus 1, and then we multiply by the natural log of whatever base we're working with. Now, in your homework, you're going to get some examples where you need to take the derivative of some function and the log will be involved. So let me just give you an example and then say where I'm getting at. So, well, actually, let me put a heading here. So let's say using log rules to simplify, derivatives. So let me just start with an example. Let's say that our function, we've got f of x equals, let's do natural log of cosine cubed of x. Now, what you could do is just apply the formula that we have, right? The one that I just erased says take the derivative of the inside function, divide it by the inside function, right? And there's your answer. But in doing so, it forces us to use an additional chain rule because you'll have to take the derivative of cosine cubed. So if instead we remember a certain log rule, we can rewrite this as 3 times natural log of cosine x. And notice here, I did not take a derivative yet. All I did was simplify. This step right here is simplifying using, I guess it would be log rule 3, or log rule C. Now I can take the derivative, and I just made life easier. I simplified my function. And so now when I take the derivative, I'll get a 3 times negative sine x over cosine x. That's equal to, when you could write this as a negative 3 tangent x. Either of these answers is fine. On a test or a quiz, I would accept that answer right there. All right, so what you want to be aware of is that by taking advantage of some log rules, you can make derivatives much easier. So let's try another example. Let's say that our function is, let's say we've got y equals natural log of square root x plus 1 cubed divided by x sine x. Now, if you don't use rules of logs to simplify this, right? To compute the derivative, you'll have to use the chain rule. And so you'll need to then take the derivative of the inside function. To take the derivative of that inside function, you're going to need to use the chain rule because we've got a square root of some function, right? So there's 2 chain rules already. Now, in that process, you're going to have to take the derivative of the inside, which will require you to take the derivative. We've got quotient here, so you have to use the quotient rule derivative of the top, derivative of the bottom. Taking the derivative of the top, you'll need another chain rule. Taking the derivative of the bottom, you'll need a product rule. So I think that was 3 chain rules, a quotient rule, and a product rule just to take this one derivative. So what I want to do instead is take advantage of my log rules. I'm going to simplify before I compute the derivative. So first, recognize this is a natural log of x plus 1 cubed x sine x, all raised to the 1/2. And so when I simplify, the first thing I'm going to do is bring this exponent out front. That gives us a 1/2. Okay, so now I've got natural log of x plus 1 cubed. That's a 3 natural log of x plus 1. Remember, when you divide, you subtract, so it'll be minus natural log of x minus natural log of sine x. I have not taken a derivative yet. All I did was simplify using log rules. Now I'm going to compute y prime. And trust me, this derivative is much easier to compute than if I would have done it directly by just applying chain rules and quotient rules and product rules, right? Notice here I've eliminated all use of product rules and quotient rules. And so now y prime equals. So this will be a 1/2 times 3 times 1 over x plus 1. That's the derivative of the first piece. Minus 1 over x. That's the derivative of the second piece. And then we have minus cosine x over sine x. That's the derivative of the last piece. So that's a good place to stop here. And so we've learned our formulas for taking the derivatives of log functions. And I should emphasize here, it's not necessary, but since we learned these log rules, using log rules in conjunction with differentiation definitely simplifies the matter, right? It's very important, right? It makes life much, much easier. So, okay, we'll see you next time.